Okay, guys, so what we are going to start working on today is finally we're going to econometrics, okay? And so what we're going to be discussing is the basics of the basic model, that is ordinary least squares model. So let's discuss about the ordinary. Okay, from now on, simply the OLS model. Let's start by defining what is the ordinary least squares model, okay? And this ordinary least squares model, guys, departs from the simple observation of the following. So imagine that I have here my x variable, I have here my y variable, and I have a series of points like in a scatter diagram. Right? So what we are going to try to do is we're going to try to find a line that fits this data here. So basically, perhaps we're going to create a line that looks, I'm sorry, should not be like that. Should be kind of center. Okay, and this one here is something I will call y hat. It's going to be the estimated line that best fits, linearly best fits these data points, right? And so the basic assumption here then is my first assumption is then going to be that this model is a linear model, linearity. Right? So in linearity, what I mean, guys, is that we're going to have a model something like that. Yi is going to be alpha plus beta xi plus an error. Right? So the model is not a deterministic one. So we're going to observe errors. Right? And what is an error? It's simply the distance between, imagine this point here. If you project this point here, this corresponds to xi. That is related to yi. And the distance between the observed point and the line, the fitted line, is what we call error I, right? And of course, you have a bunch of errors, and some of the points are going to go here. Okay, so this error is going to play a very important role here. So I will discuss this later. Okay, but linearity doesn't mean only this type of models. Linearity also can be, let's say this is A model, B model. I can also have a model like this. So I can say that this is equal to E x to the beta. Okay, so how do I linearize this model? If I take ln for both sides of the equation, I will have, remember that ln, okay, let me write everything, xi to the beta power. So these are properties of ln. If you have a product, you can divide this as a sum. So it's going to be ln of alpha plus ln of xi to the power beta. And remember, another property of ln functions is that the power of the variable simply goes out. And so basically, you can end up having a model like ln of alpha plus beta ln of xi. Okay, this is what is called a log-log model. A logarithm model. Okay, it's also linear. You can see what we have done is we have linearized the function. So you can apply also here the OLS model. And here beta, as we're going to see in the future, beta is going to be interpreted as the elasticity coefficient. Now, there is another way of having linearity, guys, that sometimes appears in real life. It's going to be simply, if we have a model like this, exponent of alpha plus beta xi. So if I take the ln of both sides of the equation, I will obtain this linear function, right? This linear function called, guys, is called semi-logarithmic function, okay? The other thing that you need to be remember, and we're going to discuss that a lot, the linearity here is the linearity on the parameters. So what it means is that what I care is having b, not b squared, not b cubed, but I can have x to the power 1, x to the power 2, x to the power 3. So there is nothing that prohibits OLS models to work with powers of the x variables. What we cannot have is powers of the coefficients of the parameters, right? Okay, so now let's continue with the main assumptions of the OLS. Okay, we know linearity is the first one. The second assumption that we are going to be working with is that the sum or the expected values of the errors are going to be zero. Right? So this implies that basically my line is a kind of center around all the errors in such a way that what the errors up, the sum of the errors up more or less equals the sum of the errors down. The third assumption that we're going to be testing later is that the covariance of the errors, error I with error J, is going to be two pieces. It's going to be zero for all I different than J. So this implies that if it's error 1 with error 2, error 3 with error 4, etc., I'm going to have a correlation equal to zero, covariance equal to zero. Okay, so this is what we call no autocorrelation. No autocovariance. Well, we were talking about covariances, so technically it should be no autocovariances. And it's going to be a constant that we call sigma squared when I equals J. So, and you can see it's a constant. So the variance is going to be always a constant. And this is what we call homoscedasticity. So these assumptions are crucial because we're going to be testing later to be sure that our results are consistent and are well behaved. Our next assumption, guys, is basically related how the errors relate with endogenous variables, with exogenous variables. And by construction, this is going to be zero. The requirement of the assumption is going to be that the covariance between EI and XJ equal to zero. This condition is known as orthogonality. Orthogonality. Got it? And what we're going to see, guys, is that when this condition is not satisfied, we're going to have a problem that's called endogeneity, okay? And we are going to require new models to solve for that, GMM models, for example. The final assumption is that what we believe is that my errors are going to be independently and identically distributed as a normal with mean mu and variance or standard deviation sigma. Okay, so this is my other assumption. So what is the meaning of that? Let's take a look to more or less what happens. So let's do a, hopefully this works. Let's do a kind of a 3D graph. So this is my X, this is my Y, and this is my probability here. And then basically if I do my X and Y, so I can have a bunch of errors, and then I can create my fit. Sorry, my fit is always, so we have other errors here. And what is interesting, what I believe is that each error really is part of a normal distribution. Okay, so this error is also belongs to other normal distribution. All centered at zero and a given standard deviation. So basically any error that you can find belongs to the same normal distribution. The same family normal distribution. Okay? So this is the fifth assumption that we are going to be basically working with. Now we can go into some mathematics. So remember, what is crucial here, we're going to pay our attention now in order to determine my coefficients. I want to determine the coefficients of y hat, okay? And in order to do that, what I will do is I will basically work with errors. Now, take a look here, guys. This is this one here. So if this is yi, this is xi. This point here corresponds to, oh, sorry, yi hat, okay? And then what we can argue, and you tell me that yi is simply y hat I plus my error, okay? So let's keep this in mind and let's move to the next page. So remember what I told you before, that yi equals yi hat plus my error. And yi, guys, is going to be, yi hat is simply going to be a plus bxi plus my error. So what is a? An estimated value of alpha. What is b? An estimated value of beta. Okay? So, and what I will do here is I will simply move my errors to the left. or stay my errors, keep my errors here, and then I move A and B, xi to the other side. So I have something like this one here. So my OLS criteria, so what I want to do in order to find A and B is what is my OLS criteria. So what I will try to do, guys, is I will try to minimize the sum of the square of my errors. Okay, so if I do that, what I need to do, I do the sum left side, sum right side is square, left side is square, right side, minus bxi square. And what I want to do here is I want to minimize this function. Okay, it's a quadratic function. And subject to what? Subject to basically A and B. Okay, so basically what we're going to do is we're going to take the first derivative equal to 0 with respect to A, and then with respect to B. And then from here, as you're going to see, guys, we're going to find two equations for A and B. Right? Okay, so let's do the derivative of the sum of the errors respect to A. Okay, so let's apply the chain rule. So it's going to be 2 sum of yi minus A minus bxi. And as soon as I'm deriving respect to A, I have times minus 1, and I equalize this to 0. Okay, so these are constants, so they disappear because I have a 0. And I end up having simply sum of xi minus A minus b of xi equals 0. Now, this condition is really important, guys, because this is related to the, I think it's the second assumption of the OLS model. Take a look. So what is this part here? If we see here, this is the definition. So this is the definition, this part here. So basically this condition here simply tells us that the sum of errors is equal to 0. So remember that the expected value, okay, or the mean is simply this one here divided by n. So if we have this part equal to 0, by construction, then guys, the expected value is going to be 0. And this is going to be true if and only if we include the intercept in my equation. Okay, so just keep this in mind. So by construction, the expectation of the errors equals 0 appears here. Now let me continue then with the math. So what I do here is I can divide the sum. So it's going to be sum of I. When you sum n times, so let's do this I equal 1 to n. When you sum n times a constant, it's simply n times a constant. Agree? Minus b sum of xi, and this is equal to 0. I will keep a here in the left. I can divide everything. I can divide and multiply this by n. I can divide and multiply this by n. Okay, so what I will have here is n y hat. Y hat is the mean of y. Minus NA, well, I should have done this easier, minus B n x bar equals 0. And then you can see that n is constant in all the elements, so this can disappear. And from here, guys, A is going to be simply equal, n disappears in all sides, because when A goes to the other side, the n goes to divide everything and they disappear. It's going to be simply equal to y hat minus B x bar. So we got here our first equation. Okay. So basically the y-intercept, our A in this equation here, is simply going to be, it will depend on the mean of y and the mean of x and the b value, that is all the other parameter. So I need to find the other parameter first in order to find A. So let's do the second parameter. Let's find the second parameter. Now what I will do is I will derive my sum of a square of the errors with respect to B. So let's do the same. It's going to be 2 times sum of yi minus A minus bxi. Now I'm deriving respect to B, so times minus xi equals 0. So the sign with that 2 can disappear. So I end up having sum of yi minus A minus bxi times xi equals 0. Right? Another note here, guys. Okay, so this was a note. I will rewrite this one here. So this one here, oops, sorry. Let me delete this part. No, I didn't want to delete it all. So this was so this part here are the errors. And this part here, of course, is xi. So if I rewrite this one here, so what I'm saying is sum of xi equals 0. Okay, so what is the meaning here, guys? Remember, I told you that the covariance of ei xi equals 0. So this is the condition that is crucial for that, right? We're going to show you, I will show you how this works in a couple of minutes. Okay, so let's continue then with the derivation and let's try to find the value of b. What is the mathematical formula for b? So I will operate this one here. So I have xi, yi, and multiply this by this, minus a sum of xi, minus b sum of xi squared, and I want this to be equal to 0. Got it? Now, I know a, so a is this one here, so I can do that. So this is going to be of sum of xi, yi minus y hat minus b x bar. This is a that multiplies. And what I will do is I will do this trick and minus b sum of xi squared and equals 0. Okay, so I have sum of xi yi minus, this is n times x bar, so it's going to be n times x bar y bar, minus plus minus, minus times minus is plus. It's going to be n, because I have this n, b x bar squared. And then minus b sum of xi squared equals 0. So what I will do is I will move all the elements that have b to the left, sorry, to the right, and keep this part here. So this is going to be equal to sum of xi yi minus n x bar y hat equals b, this common factor, sum of xi squared minus n x bar squared. And then finally, guys, so your b is going to be simply sum of xi yi minus n x bar y bar divided by sum of xi squared minus n x squared. Okay, with very simple math, guys, this one here is going to be exactly the same as this one here. If you can do the math here, it's very simple math. Divided by sum of xi minus x bar squared. Okay, so here I have my formula for b. Okay, so if you realize, guys, what is the upper part and what is the lower part? The upper part, guys, simply is the covariance of xi, yi. And what is the lower part is simply the variance of xi. So this is the famous beta, or the famous b. Okay, it's simply the relationship between covariances of xy, yi divided by the variance of xi. Then, guys, we're done. So we can compute b. Okay, this is a mathematical formula. You have the numbers, you have x, you have y. And then once you have b, you simply plug this b in here. Y bar and x bar are simply the means of the observations. And then you compute a. And once you compute a and b, you can have your y hat. This is your y hat. Remember, this part here is my y hat. And what is my y hat? Well, my y hat is simply this line here. Do you see? So we have estimated the line. We know a is going to be my y-intercept. B is going to be my slope. So I have defined my y hat. And that's it. So this is the OLS model. And before moving into eViews or Excel or R or whatever you want to use, let's do some very interesting tests that we do for the goodness of it of my model. So let's start by drawing a graph here. oops, terrible graph, but I have X and I have Y. I will do only one line. Okay, so I will do my Y hat is here. And I will say that my point, this point here, corresponds to Xi. I will just analyze one point. And this point corresponds to Yi, right? Of course, let's assume that here, this point here corresponds to X bar, and this point corresponds to Y bar. Okay, remember the line always crosses in this point, always. Right? Now, I will define this one here as usual. This is my error. I will define this part here, okay? This part here, as you can recognize, is simply Xi minus X bar. And this part here, so, and I will call this kind of a strange X, okay, Xi, small Xi. And this part here is what is simply, sorry, from here to here, this part here, I will call it, that is basically Yi minus Y hat. I will call it small yi. Okay. And what is Yi? Yi is going to be simply Yi. So there is that minus Pi. Okay. And what is important here, guys, remember this one here is equal to A plus Bxi. Okay. So what is the slope here? The slope in this part here of this part here, I'm going to use this one here. The slope, okay, B is going to be equal to Yi hat, correct? This part here, opposite by adjacent, divided by Xi. So remember this Xi is the mean. So I remove the mean from here. So from here, guys, I know that what Yi equals E of Xi. Okay, so let's call this one here 1. I also remember this one here. And then I will use, let's call this 0. So let's start using 0. I will reorganize this one. Yi equals Yi hat plus my error. Okay. And what I will do is I will simply sum and square each of the elements. So this is going to be sum of Yi squared plus sum of Yi hat plus Ei squared. So I'm doing both sides of the equation, so nothing changes here. Sorry, it's not plus, equal. And then from here, what I will do is I will simply operate a little this one here. So it's going to be sum of Yi hat squared plus sum of Ei squared plus 2 times sine of Yi Ei. And I will decompose this one here. So this is this is I hat. Remember, this one here can also be named as sum of B is a constant, goes out, Xi Ei. And remember this part here by model construction equals what? Equals 0. Okay, so just remember, I think I've done this in here. Take a look to this part here. Got it? So by construction, guys, this part is 0. So we are left with what? Okay, I will fill out this one here. Square. So finally, guys, from here, I have my simply the sum of Yi squared is the mean. Okay, so this is this Yi, remember, is the observation minus its mean. Is going to be equal to sum of Yi hat squared plus sum of errors squared. Okay, so this is called the sum of squares of total equals the sum of the squares of the regression plus the sum of the squares of the of the errors. Right? So this is one of the questions that allows us to basically understand how good the fit of the model is. We have two ways of seeing the fit of the model. We have the R-squared. Okay, so what is the R-squared? Simply what percentage of the variation of y is explained by the variation of the exogenous variables of my fit. And this implies simply my R-squared is going to be defined simply R-squared is going to be SSR divided by SST. Of course, that's why we want this to be close to 1. If all the variation of y is explained by the variation of variation, this value is going to tend to 1. Right? I can rewrite this one here as from here you can see that SSR is simply SST minus SSE divided by SST, and finally you obtain the formula that we normally use is so R-squared equals 1 minus SSE divided by SST. Okay, so now this measure, guys, is good when you have large sample sizes. However, when you don't have large sample sizes, guys, you always want to adjust for sample size. And what you do is, what we are going to create is something that's called the adjusted R-squared. Okay, so what is the adjusted R-squared? It's simply the R-squared where we divide the coefficients. So we divide SSE by its degrees of freedom and SST by its degrees of freedom. SSE has n minus k degrees of freedom, and SST has n minus 1 degrees of freedom. Right? So what is k? K equals the number of regressors or parameters. Let's call it parameters better. Number of parameters, including the constant. Okay, so what is n? Is simple, the sample size. Okay, so n is simply my sample size. Okay, so this is your adjusted R-squared. Remember that your adjusted R-squared works better when you have small samples. But as you can see, if n is very, very large, n minus k divided by n minus 1 is going to disappear. You're going to cancel out. It's going to be equal to 1. So when you have very large sample sizes, guys, the R-squared is going to be basically the same as the R-squared adjusted. Okay, so just remember that. If you have large sample sizes, both of them are indifferent. But if you have small sample sizes, what you need to use is basically the R-squared adjusted. Okay, and then you have another way of testing for goodness of it, and it's called the ANOVA test, analysis of variance. Okay, what you need to understand here is that my H0 here is that there is no linear relationship. This is my null hypothesis. There is no linear relationship between X and Y. Okay, so this is my null hypothesis. My test, guys, is going to be an F test. Okay, my F test is going to be simply sum of squares of the regression divided by its degrees of freedom divided by the sum of squares of the errors divided by its degrees of freedom. So this is one, sorry. This one here is going to be, we simply divide this by k minus 1. The degrees of freedom of my regression is k minus 1. The degrees of freedom of my errors, as I mentioned to you, is n minus k. And so this is going to be distributed as an F distribution with k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator. Okay. So what is next is basically with these tools now, guys, we can go into any program and we're going to start working on real data. Okay, we're going to start analyzing all the hypotheses. We're going to see what happens when we violate one of the hypotheses, what are the solutions, etc. This is what is going to be in the next class. Okay, thank you very much, and we continue discussing this. Please study this.